I'm Mike Bankman, the CEO of OneSpin Solutions, and just to get started, I will talk about how we can leverage simulation informed coverage in UCIS and what our plans are in doing that. I will focus a bit on observation coverage and explain what that means and how that relates to what you're doing right now with simulation. Maybe nobody or not everybody knows about OneSpin, so just a few sentences about the company. We originated from Siemens and later Infineon and have been in the formal verification space since a very long time, have put lots of engineering effort into tools and are on the market for quite some time now. We have several tools in the formal space, and one thing that I want to focus on today is our assertion-based verification flow, which we have augmented with a coverage solution that can tell you for your assertions how much of your source code has been verified, and that is exactly what you want to have in your UCIS database. And what's the problem with coverage anyway? So if you look at a verification that you do usually today, then you have a patchwork of coverage information, and you have, for example, bug discovery rates or project schedules, and say it looks okay, you can tape out, or maybe you have some coverage data somewhere, or you just guess, or do all the above. Well, the question really is, how do you really know when your design is verified appropriately? So you can apply different techniques. Constraint random, you can have critical design areas verified with formal. You may think that some third-party IP is fully verified, or also employ some rule checking solutions, and you also use your old code. In the end, you want to bring everything together and have a coverage closure. So what your flow looks like, or should look like in the end, is something like this. The ideal methodology would be that you have a verification plan and you have the right tools to be applied wherever you need them. Some blocks may be very well suited for formal, others might be better done in simulation. And in the end, you want all the coverage information unified and have your plan iterated based on coverage. So you really want to have feedback on several levels of your design and verification flow into a coverage database, and UCIS is a way of doing that. And that's why I think this is very important to talk about how we can actually interface also formal with the UCIS database. So you really want to make full advantage of all technologies available and want to eliminate some redundancies also in the testing. And coverage is a way of telling you where you really need to focus your verification efforts, where you have done a good job and where you still need improvement. I'm going a little bit more into technical detail now on what does coverage mean actually. And what you have been experiencing in the last couple of years, tens of years, is a way of verifying designs by testing, where you basically apply stimulus to your DUV and check what the results are doing. So you have a very good understanding of how good your test vectors are by looking at the coverage data that you accumulate during your testing. So what does it mean? It means that the coverage tells you basically in simulation how much of your design has been stimulated, how much has been exercised. So you really see, do you exercise all the scenarios? You can measure that with functional coverage in System Verilog. You can also apply other metrics like statement coverage or branch coverage. In the end, you still don't know how good your checkers and assertions are. So no matter how good you exercise your design, it really depends on how good also the tests are. Did you really check all the output that is produced by your DUV? And the question of finding out about this, we call observation coverage. So it focuses on the quality of the checkers, not on the stimulus. And this exposes the unverified parts of the DUV. Now you might think, isn't that almost the same? So let me give you an example. If we look at control coverage or simulation coverage as such, then you basically run through your design, and if you take the example here for a statement coverage, you basically see that the statement has been reached by your simulation. And you can put that into the statement scope into your UCIS database and say, okay, you increase the count of that bin by 1 if you have exercised it once. Now, that's good. I mean, it's something. The question is, if a statement has not been reached during a verification, of course, it can't break any checks. So you really want to make sure you exercise as much as possible. Now, if a statement has been reached, though, would some check fail actually? And obviously, that's not really the case necessarily. So you want to know how good your checkers are. And that's what observation coverage is about. So if a statement is modified, for example, in your design, and you have verified your design thoroughly, then you should probably expect some of the checks to be failing. And if that's not the case, then you may have exercised this piece of code, but you actually didn't verify whatever happens there. And in this case, the observation coverage metric that I'm going to show you here is the quantify metric in OneSpin, where we actually replace right-hand side of each of the statements with a free variable and check whether you break any of the assertions. And this way, we can measure the coverage that you achieve by the assertions that you write. So instead of just asking, have you been there, we also ask, what have you done there? So you really want to have both. You want to be there and you want to do something. And in this case, it means you want to exercise code and you also want to check whatever happens when you do that. I want to give you an example how it works in a very, very simplified version. This is a simple module, we call it M, where we have a few statements here, 5, and a very simple assertion that is actually pretty trivial, saying that whenever I get 001 on the input, then the Z is actually in the next cycle the previous value of the input A. So very, very simplified version of the design. And you may exercise, and in formal that's obviously always the case that you exercise a lot, basically everything. In the simulation you run through all this code, of course, but what you verify is actually just one statement, and the others are not covered. So how do we find out about this? Well, we just collect all the locations or assignment statements here and number them 1 to 5. And then we modify the design in principle. The prover is a bit more smart on that, but that's how it in general works. So we make 5 versions of the design, and in each case, change one line or one statement and add a free input. For simulation, that's really not so easy. So there may be other things that you might want to do if you apply this kind of scheme in the simulation space, but for formula, it's quite simple to just add an input. Has some advantages because you never can create any problems with assertions not triggering anymore. So you basically add more behavior and you say, well, if I allow more behavior, is this really failing then? If that's the case, the specification is not tight enough if I can do whatever I want. And in this case, the assertion will fail for the modification M2, and for the other, all the assertions will still pass. And that's how we just measure this. We just collect them and say, okay, the assertion covers this line. Now be sure that you understand that here, for simulation, if you just run the design and you exercise everything, all the lines would be covered, but just one line would be verified. So it's a much stronger metric, but it's also still on a statement basis. So it ties very well into this understanding of exercising code. To give you an example how far you can get, there are several things you can do here. One is you start applying this scheme on a module basis for a single designer. For example, someone writes a FIFO or a DDR2 controller or some small processor core, an arithmetic block. The runtimes are in hundreds of seconds. If you go for formal sign-off for larger blocks, up to 60,000 lines of code, no problem. It takes a while to run, but for sign-off, that's not a big issue. So companies like Infineon adopt this methodology for their formal sign-off. Now, how does this relate to UCIS? And that's basically the core of the talk. If we look at control coverage, we basically measure where we can go. So you either reach a statement or you don't. There may be two more reasons why you don't reach a statement. That is, you have either over-constrained your design, so it's constrained out. The constraints are so tight that you cannot reach a certain location, or it's actually dead code. And this is uncoverable and not executable. So whatever assertion you write or how much you want to change the code in the space, if it's not reachable, you don't actually can verify anything there. So we want to exclude this from our analysis and call this unobservable and save this data for later. If we reach some code, that's nice, but do we really verify it? That's done by the observation coverage metric I just have shown you, and we can measure whether we observe something or we don't. And there, of course, is also the case in formal that sometimes you don't know or you don't know yet. So if you start out running the coverage analysis, you would start with an unknown state. Now you can merge all this into one view, and that's what I want to see at some point in the UCIS database, that you can actually not just talk about the execution of some items like whether I have executed some statement, but also whether I have actually done some verification on them. And in the scheme, you see that you can actually merge these results back and forth, and some information travels one way and the other travels back. For example, if you have observed the statement, of course you have reached it, and that can actually be proven by the formal tool by producing a trace that demonstrates that. So this is the way it should work. Now, how does it work right now? UCIS is a good start and a really good idea. It has a reasonable definition and is also extensible, and it works well for simulation and control type of coverage. What we can do today is we can, of course, take the reached locations. I take the same color coding as on my table before, and that directly translates to coverage bins, in this case statement scopes. And we can put this in there and say, look, we have exercised this during our formal analysis. Very nice. There's also some extensions that we talk about now on having unobservability, so that in constraint code, and I want to collect coverage excludes in our UCIS, also something that you can do. If you look at covered or observed data in the sense of quantify, then this translates to covered bins, but you lose information here, so you really just remember in your database that you have actually exercised it. And of course, there are things like user-defined bins, so that's what you would need and what you would need to do right now in UCIS. However, that's not really what you want to do there because it's a different type of coverage and it's a principal difference. However, it relates very well with the things that are already there, so an extension is needed. And then there's, I have to say, right now still weak support from the big three on these coverage databases. Mentor makes a lot of effort there and others as well, but there's still a lot to do. Let me explain a little bit what we would like to see here. If we talk about the binary API, then there's lots of issues that we have to solve. For example, first is the access to the tool in the libraries. So we make sure that the integration actually works for our customers. The second thing is if you have this binary API and you get a crash or a failure on this binary API, how do you debug that? How does it work? And the way out would be to actually have the XML, the text-based data, not just exported from other tools, but also imported. And of course, this is a challenge. Right now, we face the issue that many databases can be accessed by exporting data, which is great, but you don't get this data that our tool or other tools produce back into one of the standard flows of the big three. And maybe I'm wrong, so maybe I'm not on the up-to-date status here, but that's the status that I have. And therefore, we are actually looking into changing that by working with TVS on a tool that can actually merge the different sources together and display this information. If you want to learn more about it, how this works and apply it hands-on, there's a free workshop at the IMEC Academy in a few weeks where you can actually try this yourself. If you have interest, you go to our website and find it there. Last remarks, coverage is critical to verification closure, and people need multiple tools, so integrating all this coverage data is really important. The observation coverage is something really unique and practical, and that's something that you want to have in your verification flow. To get all the information from different tools together in one unified view, OneSpin and TVS are working together on a coverage verification management solution, and if you learn more about that, ask Mike. Thank you very much. Any questions?
So we'll go to questions. Are there any questions from Bristol? Julia, you want to go first?
Hi. Do you have any plans to do kind of similar there for functional verification?
Yes, of course, you can also extend this to functional verification, and we are working on this, yes.
Question from Bristol, from Paddy.
It seems, it reminds me of something like fault coverage, but for assertions. And
yes.
With your problems that you have with getting integration with the UCIS database, I wonder if the UCIS, if the current standard allows for the saving of, say, stuck-at fault data.
So as far as I understand, it does not, but maybe Darren is better qualified to answer that. So I don't know.
Darren's shaking his head and saying no. So
yeah. So there's still a lot of things that the UCIS can or could have on standard, say, industry standard coverage types that are not in it yet. So there's still some room.
And speaks from Bristol as well.
I'm saying there's certain things that are actually in the database itself and defined. So, you know, a particular coverage metric would be defined with all of its flags and attributes associated. And then there's coverage metrics that can be extended, and anyone can decide what they look like, but then that would need to be standardized again, right? So there are levels of standardization.
I guess the issue, especially with stuck-at fault coverage, is that there are tools that are there that don't use the UCIS database, and if they all want to, you've got to make sure that they. It would be nice if they do it in a standard way. Thank you.
Any more questions from Bristol? There's one question from online. The quantity coverage, the quantify coverage seems to be similar to the method of synopsis certitude. Are you cooperating with them in driving UCS standardization towards observation coverage? Are there any cooperations with them so that the coverage gets more comparable? So I guess that's a question for OneSpin regarding working with synopsis on certitude to study to standardize this type of coverage.
Yes, we are working with synopsis right now on this. The coverage types are similar. It's a kind of observation coverage, the quantify metric, and the mutation coverage that certitude is doing. They're actually compatible in a sense. There's things that where they differ, but in a sense they both relate to what I call observation coverage here, and it would be the same scheme, and they would find out in a different way, but it would probably solve a similar question. Actually, there's customers doing both, running OneSpin quantify first because it gives a quicker view on the coverage, and then add a more long-running synopsis coverage analysis on the code. And we work together on defining goals for UCIS.
Okay, thank you.